So, welcome to the final video number 7 in our course on ST9 Exploratory Data Analysis. We're talking about UMAP, Uniform Manifold Approximation and Projection. So this is a method that is stochastic and therefore may vary around the different outputs that you might use unless you use the same seed, as nonlinear in terms of the way it transforms the data. It searches for low dimensional projection reflecting the high dimensional structure. It assumes that the data is uniformly distributed on a Riemannian manifold. It assumes the Riemannian metric is locally constant and is approximated as such. And it assumes that the manifold is locally connected. So there's a few fundamental assumptions about how we might want to use UMAP. Relative to TSNE, it is faster. It captures distances between clusters less badly than TNSNE, but is not as reliable as PCA nor as MDS. The numbers, neighbors, and minimum distances are key parameters for modeling, and therefore we have to plot how much these varies when we are using UMAP. It's very good at looking at high-dimensional gene expression data. So, for example, single-cell RNA sequencing data or spatial RNA sequencing data, it's very good at that. And it's very good at working on large data sets where some global structure is needed. So the n neighbors is how many nearest neighbors each point considers. The more data you have, then the more that can be higher. Small values of this tend to give very local structures only that are very tight and separated clusters, whereas higher values tend to give more global structure and show a broader layout. Between these two is probably a good starting point for typical samples of 100 to 1000 samples. The min dist refers to how tightly points are packed together in two-dimensional space. So if that value is very small, we tend to get very tight clusters that are good for identifying subgroups. If they're large, they'll be more spread out and it's better for visualizing gradients. And somewhere in between is kind of a good default starting point where we might try different values to see how well they work. So this is a quick summary for these different methods, which we'll talk about more in the demonstration videos, where we see that NMDS, non-metric MDS, is very good at looking at ecological data or some heterogeneous data. Permanoma can also be a nice way to link modeling formal statistical testing onto that. What we need to consider is the level of stress, how transformed the MDS dimensions are. We can also consider that if we're doing a lot of samples, it can be slow. PCA, the next one down, has interpreter axes that are needed and can be obtained, which is very useful. They can identify key features like the OTUs that are of interest, and PCA can give us a quick sense of the level of variation present. Considerations for this is that PCA tends to work on linear data. We need to transform the data first, and we need to check a scree plot too. TSNE is good for tight cluster visualization, looking at single cell flow cytometry data, and maybe finding rare subpopulations too. Intercluster distances are not real, it's parameter sensitive, and it can be slow on large numbers of samples. UMAP can be better in large number of samples and kind of balances to an extent differences between local and global structures. It's in many ways the modern default, not necessarily good, though for a lot of omics analyses. And one consideration is that it's still stochastic. The parameters it's very sensitive to parameters and not as easily interpreted as PCA or MDS. So that summarizes our brief overview of the ideas behind the different parts of this course. So key things will be to use more than one method, and when we try different parameters or patterns, if we find our output again and again, it's likely that it's much more real. Color by batch effect to check for batch effects. So batch effects would be the first thing you think about and consider, and just doing a PCA with the batches labeled is a good idea. Check your parameters and report them and optimize them. For TSNE, it might be the perplexity number of iterations on the seed you're using, and the same for UMAP in terms of the nearest neighbors and minimum distance and the seed. For MDS, we might report the distance metric and stress value, and for PCA, we might report the fractured version explained data access. So that concludes our course. Please see the demonstration videos for more.